So, hello everyone, and once again, welcome to this series of revision lectures for class 11 physics. So, we'll be continuing ahead with the topic of system of particles, center of mass, and applications of conservation of linear momentum, etc. So, this is session number 3 of this particular topic. So, let's move right ahead. So in the previous session, we discussed about the impulse momentum theorem for a system of particles. So let's once again begin by understanding or revising the whole concept of linear momentum of a system, being defined as the total mass multiplied by the velocity or center of mass, which is also nothing but the summation of mass into velocity or linear momentum of the individual particles within the system. So this is how we define linear momentum for an n particle system. For a n particle discrete mass system. In which capital M is summation of the mass of each individual particle. So it's the total mass. And VCM is nothing but the velocity of the center of mass. Now, we also saw from this definition that the rate of change of linear momentum of the system becomes equal to the net external force. Because when we sum up rate of change of momentum of the individual particles, the internal forces cancel in action-reaction pairs and we are left with the net external force. So this is the application of impulse momentum for a system of particles. And from this we see that if the net external force is 0, then the linear momentum of such a system is conserved. So this is going to be a major area of focus for us in this particular section, the applications of conservation of linear momentum. So let's get underway directly with some questions based on this. Okay, so now suppose we have a situation like this, that we have a triangular wedge on a frictionless surface. So this is a smooth frictionless surface. This is a right angled triangular wedge. Angle theta, its own mass is capital M. This is a smooth surface. This is also a smooth surface. And now a small particle is released from the position A very gently while the wedge is at rest. And it slides down towards the position B. And also given to us is this vertical height of this triangular wedge. So the triangular wedge has a mass of, let us say, 10 kilograms. And the angle theta is 37 degrees. And the height of the side column is, let us say, 12 centimeters. And a particle mass 2 kilograms is gently released from rest at the top E of its inclined surface. So what we have to do is, first of all, we want to find the displacement of the wedge by the time the particle reaches point T at the bottom of the inclined plane. And we have to find the speed of the wedge at the time when the particle is at B. So I'll just leave you with a minute to browse through this question, then we will discuss it and understand how to solve it in detail. So just take a moment to understand the question and browse through it. Okay, so let's figure out what's happening in this question. So in terms of the force picture, we can see that the moment we release this particle on the wedge, we can see that after some time, if the particle, as let's say, reach somewhere here, from the point A. Okay. So the interactive forces that are acting, the particle will be applying a normal reaction on the wedge like this, and the wedge will be applying an equal and opposite normal reaction. So if we take the particle plus wedge as a system, this is an internal force. So we are taking our system as the particle plus the wedge. Whereas external to the system are the forces that the earth is applying and the normal reaction that the ground is applying. So these they are external forces. So what we observe now, once we understand this force picture, is that all the forces acting, all external forces are vertical. Okay. So therefore, the system's horizontal momentum is conserved. There is no external horizontal force. So the horizontal momentum of the system is conserved. And remember, the system started from rest. So at this point of time, the system was at rest. So velocity of center of mass should be 0. So by the time the system reaches the situation where the particle has now reached here at the point B, what will happen is that this will be having a backward velocity, let's say V, or let's call that V1. And the particle will be having a velocity relative to the wedge, which is like this. So this is the velocity of the particle relative to the wedge. Okay. So by the time we reach the situation, the center of mass should only have a vertical component of velocity. The center of mass's x component of velocity should be 0 because horizontal momentum is conserved and equal to 0. Okay. So therefore, the system's horizontal momentum should be 0. Where we can take the horizontal axis as our x-axis and this as our y-axis. So that is going to be how we apply the momentum conservation in this particular case. And of course, work done by external forces is zero and work done by non-conservative forces is zero, assuming gravity to be an internal conservative force. Okay. So the change in kinetic energy plus change in gravitational potential energy will be zero. This will become our second equation. But in this case, we are taking the system as the wedge plus particle plus gravity. Gravity is also part of our system. So the gravitational force is internal conservative. Okay. So we have an application of conservation of mechanical energy and conservation of linear momentum. So now let's see how we will execute this. So for the first one, conservation of linear momentum in the horizontal direction. So Px for our system should be zero. As far as our system is concerned, the wedge is moving with a velocity v1. So the horizontal momentum of the wedge is equal to plus capital M v1. Okay. But the particle has a relative velocity in this direction in a frame which itself is moving at v1. So the particle's net velocity becomes the vector sum of this p1 and this v relative. So velocity of the particle is this much. Okay. So horizontal momentum of the particle is small m into this horizontal component. This much. Okay. So these are the individual horizontal momenta of the particle and the wedge. So horizontal momentum of this system being zero means we have this relation. Okay, now in this theta is 37 degrees. Capital M is 5 times small m because this much. Okay, so we can see that 6v1 is equal to 4 by 5 v relative, or v relative is 15 by 2 v1. So this is what we get from our first equation and horizontal momentum conservation. Okay, and because the horizontal momentum of the system is zero, we'll also get another important thing, that the horizontal displacement of the center of mass should be zero. Okay. So this also tells us that the horizontal displacement of center of mass should be zero. So this is going to give us a separate result also for the displacements. Okay. So we'll come back to that displacement part, but let's solve the second equation now, which was conservation of mechanical energy. Okay, so for this we have So the system is going from this state to a state where something like this, and the particle has fallen through a height of h. So half capital M V1 square plus half M into V of the particle square minus mgh is equal to 0. Okay. So in this also we just saw that velocity of the particle was this much. So we can now also substitute this where so we can substitute this term as this much. Okay. And we had also got the relation. Okay. And we had also got the relation that V relative was equal to 15 by 2 V1. So one is we have substituted this term over here. And secondly, V relative sine theta will become 15 by 2 V1 into 3 by 5. So that is 9 by 2 V1. So next is we will substitute this term over here. So this becomes V1j cap. So this is the velocity of the particle in terms of the parameter V1. So the speed of the particle is this much. Okay. So substituting that back in this equation. So capital M we can write as 5 times small m. And now we can write particle speed as this much. Okay. So we have this term now. Okay. So this will become the value of V1, which is in fact the second part of the question that has been asked. Okay, so this gives us the expression for the speed, and you can substitute the value of h and all that. Now for the displacement, of the block, we'll use the concept that displacement of the center of mass along the horizontal direction should be zero, because the linear momentum of the system along the horizontal axis is zero. So keeping that in mind, you can see that if this is where the system started from, and after a while reached here. So this is the horizontal displacement of the particle, and this is the horizontal displacement of the wedge. But because the horizontal displacement of this is zero, so m into delta x for the particle will be equal to capital M into delta x for the wedge. They are opposite in directions. So this implies this. Okay. So delta x of the particle becomes 5 times delta x of the wedge. The first equation, because capital M is 5 times small m. And the other thing becomes that you can see that the sum of these two displacements is this base length. And this base length we can calculate because we know this height, we know this angle. So h by L is equal to tan theta. So h was 12 meters, theta is 37 degrees. So L will come out to be 16 meters. And geometrically, you can see that the sum of these two is equal to this length. Okay. So from this, you can see that delta x of the wedge will become 1/6 of 16 meters, and delta x of the particle will become 5/6 of 16 meters. So this is the answer for the second part. So I'll just leave you with a minute to browse through this section also. Then we'll move on to another question. Okay, next we will look at an application of impulse momentum concept to center of mass. So this is a smooth surface. And on this surface now we have a wedge shaped like this. Which is having like a hemispherical surface on the inside. So this wedge has a mass capital M and it has a smooth hemispherical surface. Radius R. Okay. Now a particle is released from this position A. So given that the radius of the wedge is 20 meters, the mass of the wedge is 50 kilograms. The mass of the particle is 12.5 kg. Now the particle is released gently from rest at the point A. So first of all, we want to find the speed of the wedge, speed of the particle at the instant when the wedge just about loses contact with the wall. Then we want to find the total or the net impulse, the net impulse applied by the wall on the wedge. Okay. Because the wedge is in contact with the wall for a fixed duration of time. So during that time, how much force integrated over time or impulse the wall is applying on the wedge, we want to calculate that. And next we want to find the maximum height to which the particle climbs on the wedge on the other side with respect to the lowest point on the hemisphere or on the hemispherical surface. Okay. Take the value of G as 10 meters per second square. So once again, I'll just give you with a couple of minutes to go through the question, try and understand what all concepts we can apply over here. So I would advise you to again start with the force picture, try and understand what kind of interactive force acts between the particle and the wedge, and therefore try and understand what is the situation necessary for the wedge to really to lose contact with the wall. Okay. Then we'll discuss further. Okay, so as I was saying, if we try and understand the impulse picture here, what we'll see is that as the particle is coming down the wedge, so initially the wedge is in contact with this surface. But of course, after some time, it will lose contact. So we'll discuss about that also. Just a moment, we'll get back to that. Right. So initially, when the particle is coming down from its initial position till it reaches the lowest point, so it's somewhere in between over here, we can see that the interactive force between the particle and the wedge is the normal contact force. Okay. So this normal contact force has a horizontal component which pushes the wedge against the wall, and that is where the impulse due to the wall comes in. The wall ends up applying some kind of normal reaction force, let's say NW like this. Okay. And of course, because of the vertical gravitational forces, the floor is applying an upward normal contact force. Okay. So we can see this is what is happening. So at this point of time, what is happening is that the wedge remains stationary. Okay. And the particle is in vertical circular motion. A fixed circular track from the point A to, let's say, this point B. So we can apply conservation of mechanical energy. Okay. So by the time it comes to B, if its speed is Vb, so half mvb square minus mgh, where h will be equal to the radius of the track. Will be equal to 0. Okay, so this will be the speed of the particle when it reaches the point B, and the speed of the wedge is 0. It's at rest. Okay. But the moment it crosses the point B, now you can see that because the interactive force now has a horizontal component which is pointing towards the right instead of towards the left. So that's why this loses contact with the wall. And at this point of time, the wedge itself is moving with some horizontal velocity v1, and the particle has a tangential relative velocity. So basically, after crossing the point B, after the particle crosses B, the wedge loses contact with the wall. Okay. Now there are only the vertical external forces. No contact force with the wall. Okay, so this is the picture. Okay, so here we can see that from B onwards, for the particle plus wedge as a system, horizontal momentum is conserved. Okay, and the particle plus wedge plus gravity as a system, mechanical energy is conserved. So these are the two principles we'll be applying. Okay, so now if we compare the particle from the position B, where it had just about lost contact with the wall, so normal reaction with the wall had become zero, and at the point B, the particle had the velocity 2gr like this, to the point when it reaches the highest point. So where it reaches the highest point, let's say that point is C. So at C, which is the highest point after crossing the point B, okay, relative velocity of the particle will become zero. So at this point of time, the particle's relative velocity with respect to the wedge will become zero, whereas the wedge is moving at some velocity, let's say v prime, in the ground frame. So between this picture here and this picture here, we have to conserve horizontal linear momentum for the system and mechanical energy for the system. And this is the height to which the particle would have climbed in. This height h. So we have to calculate this value of h by that. Okay. So horizontal momentum of the system will become this. Okay. So capital M was 4 times small m this time. So from this we can see that okay, this is our V prime. This is what we are getting from horizontal momentum conservation. And secondly, we have mechanical energy conservation between these two pictures. So change in kinetic energy plus change in gravitational potential energy is 0. This is the change in kinetic energy. So now substitute this over here. Okay, so we'll get mgh is equal to mgr into 1 minus 1 by 5. So we get n is equal to 4 by 5. So that becomes the answer to the third part. Okay. Now we'll also discuss about the impulse. So let's get back to the solutions. Okay, now to calculate the impulse due to the wall. So the second part of the question, the net impulse by the wall. Okay, so that will be this normal reaction that the wall applies for the time in which this is in contact. The particle reaches the point P. So if you look at it this way, when the particle started from the point A, the momentum of the system was 0. Okay. And from here, right, so at this point of time, the momentum of the particle, momentum of the system was 0. Okay. And by the time the particle reaches the lowest point B, the particle itself has a horizontal velocity, whereas the wedge is at rest. So the momentum of the system has become MBB. Okay, and this is the time for which the wall is applying contact force. Now this contact force becomes 0, and after that the wedge loses contact with the wall. So this quantity is the change in horizontal momentum of the system as the particle goes from A to B. So the impulse applied by the wall will become this much. So this is this part of the question. Okay. Okay. Now next example, we will pick up something where we apply concept of momentum conservation with a spring involved. Okay, so let's look at this question next. Okay, so mass of A and mass of B is 2m, where m is equal to 1 kg. A spring of constant, let us say 25 newtons per centimeter, is attached to B, and A fits the spring at a speed of, let's say, 2 meters per second. So we want to find out the maximum compression of the spring. And the final velocities of A and B after the spring releases A again. Okay. Or you can say the spring disengages from A again. So I'll just leave you with a moment to go through this question, then we'll discuss. Okay, so let's understand this question next. Okay, so let us finally go through this question and understand the application involved. So basically, see, what is happening is that at any time when, or rather at the instant when the block A is about to hit the block B, A is about to hit B. So X of the spring is still 0. The velocity of B is still 0. But A is moving with a velocity of V0. And there is no interactive force here. But from here, as we reach an intermediate stage where A is impinged or compressed against the spring, therefore the spring has also pushed B. So B is also having some displacement by now. So now if we compare this state of the system with the earlier state of the system, here the spring was at natural length, but now the spring is having a compression. And by now B has a velocity Vb and A has a velocity Va. So comparing from here to here, we can see that the system's momentum is conserved. Okay, in fact, horizontal momentum is conserved. There is no vertical momentum. Okay, because you can see that the interactive force is the spring force. So equal and opposite spring force is acting on A and B. Okay, so there is no net external force on A and B put together. So okay, or so at any instant, the relationship between VA and VB will be like this. This is our first equation. Okay, and then there is energy conservation. For A plus B plus the spring as a system. This is for A plus B. Okay, so conservation of energy here will give us so that's our second equation. Okay, so now we can see that for the first part, we want to find out the maximum compression of the spring. So that is, for that we have to understand that initially, for some time, VA is greater than VB. So A approaches B. The distance between them is decreasing. Eventually, after some time, B picks up more speed than A. So A and B start to separate. Okay. So therefore, X is maximum. That is, A and B are closest at the instant when VA is equal to V. So this is the condition for the spring to have maximum compression. So applying that condition, now we can see that from equation 1, VA is equal to VB implies that the common velocity at that instant will be V0 by 3. And substitute that in equation 2. So A is kinetic energy plus B is kinetic energy is the initial kinetic energy. So we can see So we have this relation now. This will be the maximum compression, and we can substitute the values which are given. So I'll just leave you with a moment to go through this once more. Okay, so momentum conservation, energy conservation, and then applying the condition that when the spring has maximum compression, they should have common velocity. Okay. And like that, the second part of the question now is when the spring disengages, you want to find the final velocities when the spring is relaxed again. Okay, so x is equal to 0. So from equation 1, from momentum conservation, we had, this was equation 1, conservation of horizontal momentum. And we had this was equation 2, conservation of energy. So in this we put x equal to 0. So we have VA square plus 2VB square plus 0 is equal to V0 square. So when we solve this equation together with this equation, we will get the solution set. V0 is, or rather VA is equal to V0 and VB is equal to 0, which we won't take as the solution because this is the initial one. Okay. And we'll get VA is minus V0 by 3 and VB is 2 V0 by 3. So this will be the final velocity. So after the spring disengages, A will be having a velocity of V0 by 3 backwards and B will be having a velocity of 2 V0 by 3 forwards. Okay, so people, with that we will be concluding today's session. And next time we will pick up collisions as the further application of center of mass and system of particles. So that's it for today and wish you all the very best.